Hey there, guys. Good afternoon. Here's an energy problem that contains some good algebra practice. We're told about a block that's moving around a circular frictionless track, and we need to figure out the magnitude of the normal force that's acting on the block once it reaches the top of the circle. Let's start by drawing a free body diagram for when the block moves through the bottom position first. At this point, the block will experience the force of its weight pulling down, as well as an opposing normal force from the track. Since it's spinning around in a circle, we should also include a centripetal acceleration vector, which will point upwards towards the center of the circle. I'm going to set the bottom of the circle to y is equal to 0, and if I move these coordinate axes out of the way for a second, we can see that at the top of the circle, the block will eventually reach a height of 2 times the radius. We'll keep that in mind for when we switch positions. But for now, let's do the sum of forces in the y direction here at the bottom. The definition of centripetal acceleration is v squared over r, so let's go ahead and plug that in on the right-hand side. We can also include a subscript b to indicate the speed occurring specifically at the bottom. Next, here's 2 steps at once. Multiply both sides by r and divide both sides by m, like this. Now, you could solve for the value of this speed if you like, but it's really not necessary. Besides, we shouldn't be approximating values before calculating the final answer. That's how you end up under or over rounding the final result. And oddly enough, that's exactly what the author of this problem does in the solution manual. And he ends up violating his own rules. So let's not do that. Instead, we can apply the conservation of energy to the block at this position. Since we said y is equal to 0 at the bottom of the circle, there won't be any initial potential energy. There's no friction on this track either, so let's get rid of the other work term as well. Here's what's left. When we plug in the energies, the goal here is to solve for the square of the velocity at the top, which is this v sub t squared variable right here. Let's move our final potential energy term here over to the left and plug in our previous expression for the square of the speed at the bottom that we had from before. To get v sub t squared isolated on the right, multiply both sides by 2, and then divide both sides by the mass of the block. With that taken care of, we can move on to drawing a free body diagram of the block at the top position. Remember, it's at y is equal to 2r now. In terms of forces, the weight will still point downwards, but now so too does the normal force from the track, as well as the centripetal acceleration vector. If we do the sum of forces in the y direction, it will contain all negative terms, but we're not interested in the direction of the normal force at the top, only the magnitude. So in that case, it's totally okay to multiply everything by -1 and work with strictly positive values. Let's move mg over to the right-hand side, and now we have an equation that we can work with. There's not a whole lot of room left here, so let's go ahead and pull this onto a fresh screen and then finally solve the problem. Before substituting anything, I'm going to pull the m over r ratio that's attached to this v sub t squared out in front by itself, since I don't want to lose anything important along the way once I start distributing. Now here's where that lengthy expression for the speed at the top squared coming back in. Let's distribute m over r inside the square brackets, which will thankfully cancel out nicely with the ratio inside these rounded ones. And don't forget to apply it to this 4gr inside as well. We'll no longer need this double set of rounded brackets, and when we apply the ratio, 4gr will turn into 4mg. This minus mg can be collected with minus 4mg, which gives us a total of negative 5mg, and the square brackets can be dropped, which allows us to collect yet another minus mg to make that total negative 6mg. Now everything boils down to something easily manageable, and there was no need to calculate velocities or anything like that along the way. Let's go ahead and plug in our numbers, and the final result is a normal force magnitude of exactly 0.460 newtons. No approximation necessary. Isn't this nice? Way better than the author's approach, in my opinion. For comparison, he resulted in 0.456 newtons, so we're right in the neighborhood of where we should be, even though we took a different approach. Thanks for watching, everyone. See you in the next problem.